Uh, we had seen the voltage swing in the last lecture. So let's look at the frequency response, one of the major advantages of common collector amplifier. So as usual, what we do is we take our amplifier, we transform it into the equivalent circuit that you see over here. And the usual capacitances are there, C pi, C mu, the usual elements, RBB. We said we need to include for high frequency response. And the dependent current source, RE parallel RL, come on the emitter side. And we have RS and RB here. All right, so that's our equivalent circuit. And as we said, one of our methods is that we find out the time constants due to C pi, time constant due to C mu, add them up, and we get the upper cutoff frequency here. So that's what we can do here. All right, so before we do that, it's easy to combine a few resistors here, RE parallel RL, redefine it as RE dash, and we can take a Thevenin's equivalent at this particular point and combine RS and RB, which will come in parallel. So we do that, we call this RS dash here, VS dash here. And so note that what we have done is, so what we have done is RS, RB, and RBB, everything we have combined together. We have combined together in one single capacitor here, in one single resistor here. And so we are left with, also note that this C mu that you see here is ground here, so some rewriting of the expression. Okay. So it's the same equivalent circuit with some resistors combined, capacitors rearranged, and so this is the simplified circuit that we get here. And as I said, we have to find out due to C pi and C mu. And let's do that. So open circuit time constant approach is, we've already seen that the resistor seen by C pi is this expression here. It's a general expression. All you have to do is substitute proper values of RE dash, RS dash, and all that here. And for the case where the resistor in the emitter is sufficiently large, so for accurate value, you just go ahead and put the values of RE and all the parameters and you'll get the value of R pi. But as an approximation, if the resistor here is sufficiently large, then this whole expression ends up as 1 over Gm. The resistor seen by C pi becomes simply 1 over Gm. And R mu that you see here, R mu, again, there's a long expression, but as RE tends towards a large value, this whole expression of R mu basically turns out to be RS dash. All right, so which leaves us with a upper cutoff frequency, so which is 1 over 2 pi, RS dash, C mu, and C pi sees R pi, which is 1 over Gm. So this is the expression for upper cutoff frequency that we get here. All right, so not much to do except that use the expressions that we have already given to you for R pi and R mu, and just use it with the values that are given here. And you get an estimate for FH. However, if you note that I put a question mark, in this particular case, we get a value for FH which is not accurate. All right, let me show it to you. Or show it to you. I'll come back to this a little later on. Okay. So when I take my amplifier and I expect for the values that are given RBB, C mu, C pi, Gm, I expect 126 megahertz, and the value that I get, if I look at, this is my normal gain, this is gain of the common collector plotted against frequency, and so this is the gain in dB here, and when I go 3 dBs below, I find a upper cutoff frequency of 3.2 gigahertz. So, which means that our prediction from open circuit time constant gives us 126 megahertz, and the value that we get from simulation, the accurate value, we get 3.2 gigahertz. So something is very drastically wrong with this. As I said, this is an approximation. This is an approximation based on a dominant pole. If you recall, we knew that there are poles and zeros and all that in my transfer function. We assume a dominant pole, and on that basis we calculate. And as I said, in most cases, the numbers that you get here for common emitter, common base, and all that is fine. But in this case, common collector, it gives us a value which is way off. And so what we need to do is, we need to go back to the transfer function. We need to go back to the transfer function, and which means that you have to go back to your circuit here, and V0 here, V0, and go back here, V0 is over here, V0 by Vs dash. So you have to write down by replacing this by 1 over j omega c pi, 1 over j omega c mu, and use KCL and KVL and get V0 by Vs, the transfer function. All right, so it will take a little bit of effort, but you can get a transfer function which is shown over here. HS is 1 plus Rs dash C mu C pi by GMS and S square here, and there is a 0 also. So this is a transfer function that you get, and interestingly what is happening if we look at the transfer function. The transfer function, what we find is that, of course, it's a quadratic here, so there are 2 poles. There are 2 poles, and if we assume that there is a dominant pole, if we assume 2 poles, if we assume there's a dominant pole, then as we had shown earlier, this term represents the dominant pole. Dominant pole, let's say 2 poles are there, FP1 and FP2. So this one is FP1. FP1 is 1 over 2 pi, this value here. And the product that you see here is FP1 and FP2, and from there we can get FP2 also. So assuming a dominant pole, I can get 2 poles here, the FP1 and the non-dominant pole FP2. So FP1 is what we have written here, dominant pole approximation. It is this particular term here. The non-dominant pole, which we can extract from here, it is this value here. And the 0 that you see here, C pi by GM, is this value here. Fz is 1 over 2 pi, C pi by GM, 156 megahertz. Okay? So we are still making a dominant pole. Of course, I can factorize this and get the accurate value of first pole and the second pole. But assuming still a dominant pole approximation, what we find is the first pole is here, the second pole is here, and the 0 is over here. And if you look at the value of the first pole, the dominant pole, okay, look at the expression here, Rs dash C mu plus C pi by GM. In this, we have already seen that C pi is a very large quantity compared to C mu. So what happens is, many times, FH is dominated by C pi by GM. The first dominant pole is dominated by C pi by GM. But you also see that the 0 is also C pi by GM. 0 is also C pi by GM. So in this case, in this unique case here, what is happening is the dominant pole, which is in the denominator, is being cancelled by the 0 in the numerator. Both are roughly at the same place here. This is 156 megahertz, and this we just calculated 126 megahertz. Okay, 126 approximate value 126 megahertz here. So these two are getting cancelled. The dominant pole is getting cancelled by the 0. And so what are you left with? The non-dominant pole. The non-dominant pole, which is 1 over 2 pi Rs dash C mu. So the non-dominant pole is at 4.5 gigahertz. So the dominant pole is where? Around 126 or 130 megahertz. 0 is around 156 megahertz. And the non-dominant pole is 4.5 gigahertz here. So the dominant pole and the 0, they cancel each other. They end up cancelling each other, and thereby giving rise to a upper cutoff frequency which is determined by the non-dominant pole, and that goes to 4.5 gigahertz, a very high bandwidth. Alright, so in this case, the open circuit time constant approach, which is neglecting the non-dominant pole, neglecting the zeros and all that, it fails. As I've said earlier, the the best way of getting a frequency response is, or the accurate way is, through the transfer function. But in many cases, in common emitter and all that, the dominant pole was at a much lower frequency than the non-dominant pole, which is also here. 126 versus 4.5 gigahertz is also true here. But the 0 also in most of the amplifiers occurs at much higher frequency. So the 0 does not matter, the non-dominant pole does not matter, and the dominant pole determined by this particular one is the one which is the key factor here. And that, using open circuit time constant approach, we are able to estimate quite accurately. So in common collector amplifier, then we have this unique situation that these two are cancelling, and our estimate just goes completely wrong. Okay. and completely wrong. And so the only thing that we can say about our in this case is that the upper cutoff frequency in such situations is determined by this factor here, 1 over 2 pi rs dash c mu. 1 over 2 pi rs dash c mu. And you can see here this gives us 4.5 gigahertz. Actual value is 3.2 gigahertz, reasonably close to what the actual value is. So 2 points to note here. Open circuit time constant is failing in this particular case. Why it is failing, I've explained. And the other one is the non-dominant pole, which is given by this expression, is the factor which determines the upper cutoff frequency. And upper cutoff frequency is very high, 3.2 gigahertz here. All right, so that's as far as the frequency response is concerned. Many times what happens is your common collector amplifier is driving not only a load resistance RL, but there may be a large CL also. Depending on the application, your load has RL as well as CL. In that case, what happens is my open circuit time constant approach. Open circuit time constant approach says RBB C mu, C pi by GM. These are the two terms that we had already determined. Now there's one more capacitor CL, load capacitor here CL, and CL effectively sees, as you can see here, RL. And when I look towards the left, I see R0. So R0 comes in parallel with RL along with CL. So you get this term also in the open circuit time constant approach. So you get one due to this, and then one due to C pi and one due to C mu. Now, if you're driving a load with CL which is significant, you know, as you recall, C pi's are in picofarads, 20, 30, 40 picofarads here. C mu is also in picofarads. If you end up driving a load CL which is 100 pf or 200 pf or a nanofarad or so, what you end up with is a large time constant here also, which you have to include as well. And then what happens is, this is the dominant pole. The dominant pole now goes to a much lower frequency. It can go to a much lower frequency because of this time constant here. So now again, if you go back, if my dominant pole here, if I add R0, CL term here, and dominant pole goes to a much lower frequency, instead of 125 megahertz that was coming here, let's say if it goes to 50 or 40 megahertz, the zero still stays as 156 megahertz. The non-dominant pole still stays at a very high value here. So again, our open circuit time constant approach becomes valid. Again, it becomes valid, and the frequency response then is no longer that great that you see here, 4.5 gigahertz, but it may become much smaller and given by this particular value. All right. So what we need to do, if CL is given to you, you need to calculate this value here, and you need to compare with the FZ value here, 2 pi C pi by GM, and you need to look at this value here and see whether there's a pole zero cancellation or not. If your dominant pole is coming out to be much lower than this, there is no pole zero cancellation here, and the dominant pole will give you the upper cutoff frequency. If the two are reasonably close to each other, then they are cancelling, and then this term becomes the determining factor. Okay. So this is something that we have to look at, and as I said, this will especially be true if we have a very large CL in my load which is present. Okay. All right. One other interesting thing about related to upper cutoff frequency is when you're driving a load, whatever RL, CL, whatever is there, the load, when it looks at the common collector amplifier from here, it of course sees a voltage which it is receiving, but it also sees a output resistance, right? When I look from here, my common collector amplifier appears to be a output resistance. But note that when I look from here, the output resistance is, we are calling it resistance, but there are capacitances here. So when you look from here, it's actually an impedance, which varies with frequency. Now, when you look at a common collector amplifier, and you look at it from here, and you look at it as a function of frequency. So I'm plotting the magnitude of the impedance, output impedance. Magnitude, I'm not looking at the phase part here. So the magnitude of the output impedance, as you can see here, this is the mid-band region here, independent of frequency. The value is pretty small, 9.5 ohms. But then as you start going towards higher and higher frequencies here, the output impedance starts behaving like this. Starts rising, reaches a peak, and there are more complications that are occurring here. Output impedance starts going like this here. Now this behavior, as you can see here, if you have an impedance, magnitude of impedance which is independent of frequency, you can say, well, it acts like a resistor. A resistor is independent of frequency. In this region, the impedance is increasing with frequency. Impedance is increasing with frequency here. And so we say our common collector amplifier is behaving in an inductive manner. Inductance is omega L, and the magnitude of the impedance increases with omega. So your common collector amplifier is behaving like, when you look at it from here, is behaving in an inductive manner. And then there are more complications. It reaches a peak and then it starts falling. But most of the time, as I said, we are either here or in this particular region. This is where you would be. Okay. So the one point which may be of, from the application point of view, may be of interest is that at some higher frequency, your common collector amplifier may appear to be inductive. Now, if it appears to be inductive, you can see that there can be potential problems. Potential problems in the sense that if I have a CL and I have an RL and this appears to be inductive, the whole thing appears to be an inductive, and therefore you have an inductor in parallel with capacitor, some kind of a resonance circuit. So it can lead to problems in your load. Okay, so this is something that one has to be aware of, as that common collector amplifier at a higher frequency, when you look at it from here, may appear as an inductive load. Now, why does it appear as an inductive load? Well, one simple way is to simply, put a voltage source here, put a current, and calculate what is the impedance, and then the impedance will show you that it varies with frequency here. But let's look at this part in a little bit more detail here. So this one is the equivalent circuit here, C pi R pi. Where is the inductive behavior coming from? So if I look at C pi in parallel with R pi, this whole thing can be written as an impedance Z, which is R pi by 1 plus S C pi R pi. All right. When I look from here, we said that the impedance when you look from the emitter side is Re dash in parallel with whatever is in this side gets divided by beta. Gets divided by beta, but it was not really beta. If you recall, it was 1 plus GM R pi. GM R pi, when we are neglecting capacitances, GM R pi was beta. But in this case, now it's no longer going to be GM R pi. It's going to be GM Z pi here. So if I calculate the impedance looking from here, it's Re dash in parallel with this whole thing that you see here, Z pi plus RBB divided by 1 plus GM times Z pi. So this is what it comes out to be. Now, if the frequencies are sufficiently high, this term S C pi R pi is, let's say, much larger than 1. So this is equal to 1 over S C pi here. So it's like a capacitor. If I plug it here in this particular term here, R0, and I try to simplify, so we look at this term here, and if we try to simplify, we end up RBB, so we put here Z pi, we put the value of Z pi here, 1 plus GM, Z pi, all that we put here. This is how R0 begins to look. And if you look at this R0, 1 over GM, that's what we said at low frequencies. If you put S equal to 0 here, S equal to 0 here, the net impedance looking from the emitter would be 1 over GM. If Re dash is large here. So we are ignoring Re dash. So 1 over GM, which is fine. But these are the S terms that are there here. So 1 over C pi by GM and S RBB C pi here. So the source of the inductive term is this particular one that you see, this term. That is what is causing, if at some frequency, what you find is that the numerator becomes a dominant. Numerator becomes dominant, and then why will it become dominant? If you look at C pi is the same. Here I have RBB and here I have GM. So let's put some numbers here. Suppose I bias it at 1 milliampere, then 1 over GM is 26 ohm. 1 over GM is 26 ohm, and RBB, let's say, is 200 ohms. So RBB is 200 ohms. So you can see here, this is 10 times larger than this particular value. So what happens is, as I go from low frequency, first this term will start becoming dominant. 1 plus S RBB C pi start becoming dominant here. Before this term becomes dominant. So you can, so that is what is happening when you go here, go from low frequency here. The numerator starts becoming dominant. Okay? The numerator starts becoming dominant, 1 plus S RBB C pi. And this is a term which is giving rise to, so when you see 1 plus S times something here, you know that this term is like an inductive term. So this is what is coming here. But after a certain frequency, this also starts matching here. So that's why you see, you go back here and then you reach a peak here. And then there are more things that are happening which pull it down, and there are C mu's and other things also that are there. So the inductive term is coming because of this part here, RBB C pi here. The larger the RBB term here, the more the importance of this particular term, the more the inductive effects that are present here. Okay. For example, in these simulations, what I did was I varied the value of RBB. So RBB is 0. We don't see any inductive effect. RBB is 100 ohms. You can see this is a plot of output impedance versus frequency here. You see this inductive effect. 200, you see even larger. 300, you see even larger here. The inductive effects that you see here. So it's all got to do with this particular term here, RBB C pi. So all you need to do is write down what is the net impedance looking from here. And if you examine it, you find terms like this, which is giving rise to inductive behavior here. All right. So with that, let me summarize about common collector amplifier, a slide which we've already seen. Common collector amplifier, and especially contrasting it with common emitter amplifier here. So this is an amplifier which doesn't give us gain, gives us high input resistance, gives us low output impedance here, gives us a good swing, 3 volt with very low harmonic distortion. So it's a highly linear amplifier, and gives us, if there is no large capacitor attached here, gives us a very high bandwidth here. FH is very high, 3.1 gigahertz as compared to a common emitter amplifier. All right, so the common emitter amplifier we recognize now, it's an amplifier which gives us gain. It specializes in giving us gain and doesn't give us very high input or very low output impedance here. This is a stage which specializes not in gain, but in giving you high input and output high input and low output resistance here. So that's the characteristics of this particular amplifier here. And common base we have already seen earlier. Okay, common base also gives you higher bandwidth, gives you a gain, but gives you very low value of Rn. So we've seen now 3 amplifier configurations: common emitter, common base, and common collector. Right? Maybe I should have what I should have done here is, common emitter, maybe use a red color. Common base, maybe I should put blue. And common collector, maybe put green. Make sense? Common emitter, red. Common base, blue. And common collector, green. What am I hinting at? RGB, red, green, and blue. RGB means what? You've all learned that these are the 3 primary colors: red, green, and blue, right? And you can mix red, green, and blue, and you can get whatever color that you want, right? So this is the whole of all the amplifiers, all these circuits that you find. Most of them are a combination of these 3 stages: a common emitter stage in some form, a common base stage, or in a common collector stage. The transistors are being used either in this, or in this, or in the common base. So these are like the 3 primary colors. Okay? And you should recognize what each one of these 3 primary stages, what are their characteristics? What do they give us? Okay? Common emitter is here, common collector is over here. Typical characteristics that you see here. Common base we have seen earlier. Okay? Uh, we also saw that common collector in the last lecture, so we'll look at it in a little bit more detail now. Common collector, where you use a resistor, is not very good. And it's better if you take a common collector amplifier and bias it using a current source. Then the characteristics improve quite significantly here. All right, so this I've said that, why are we calling it a amplifier, even though the voltage gain is 1. So it's very easy to see that it's a power amplifier. Power input that you drive in here is Vs square times divided by 2Rin, assuming a sinusoid. Power output is V0 square by 2RL. If we take the ratio, P0 by Pn is Rin by RL, and we can easily make this factor much larger than 1. Rn is beta times RL here. If I put here P0 by Pn, you can get beta. So power delivered to the load divided by power taken from the input. The ratio can be as large as beta here. So that's why we call it a amplifier. There's a power gain here. All right, let's get a better feel for this amplifier by doing a couple of problems here. So it's better if you guys all take out a sheet and work it out with me. That way you'll get a better feel rather than just listening here. And at the end of it, that sheet please submit with your name and roll number. Okay. All right. So what we need to do is the following. So this is a design problem. It's a design problem where what we are asked is that there's a common collector amplifier whose configuration is given here. And we have said that this amplifier has to drive a load of 100 ohms. A load of 100 ohms is driven by 5 volts. And for some reason, I mean, this is a hypothetical this thing, for some reason, the maximum swing that I require is only 1 volt. Okay? My load will never demand a swing more than 1 volt here. So I need to design it such that this stage is capable of giving me a maximum swing of 1 volt. You don't need to design it for 1.5 or 1 point, whatever it is, not more than 1 volt. So the issue is, how do we go about, as you can see here in this, there are only 2 variables. All you need to do is find out RB and RE. Okay, 2 variables is all that you have to find out. What is the right value of RB and what is the right value of RE? Okay, and with the idea that my voltage swing is at least as large as 1 volt. All right, so what are the relevant equations? When we talk about swing, we had one equation like this. V0 is less than or equal to ICQ RE parallel RL. Where does this term come from? Everybody should be familiar. Where did we get this from? Where did it come from? We said that my amplifier must have enough drive current. And where is this limitation coming from? The negative swing. On the positive side, we said your amplifier will always have enough current to drive into the load. On the negative side, if you don't have enough current, you'll start getting clipping. And this is what this term says. That if you want a swing of 1 volt, then that 1 volt must be less than or equal to ICQ RE parallel RL. So that's one limitation here. Now note, what I'm going to do is, I'm going to take this and transform it by saying ICQ RE into RL, RE plus RL must be greater than or equal to V0. Or what I'm going to do is ICQ times RE is the emitter voltage here. So I'm going to rewrite this as emitter voltage must be greater than or equal to V0, 1 plus RE by R. So instead of taking this term, the way we have written, I'm going to rewrite it in this form here. You'll see in a minute why we have to do this. VE must be greater than or equal to V0, 1 plus RE divided by RL. So that's one term. The other constraint on swing was coming that my transistor should not go into saturation. So this was giving me V0 must be less than or equal to VCC minus VC sat minus VE. This term I can take and rewrite it again in the form of emitter voltage. Emitter voltage less than or equal to VCC minus VCSAT minus V0. And another one of them was that we said that the net voltage at the base of the transistor, if it cannot exceed VCC, if there's a ceiling of VCC and the net voltage cannot exceed VCC here, from there we got this term here, which can also be rearranged in the form of VE less than or equal to VCC minus VB minus V0. So there were three constraints on my output swing. One coming from the drive current, one coming from saturation of the transistor, and the other coming from that the base voltage should not exceed the supply voltage. Net base voltage should not exceed the supply voltage. These were the three constraints on my swing, and we've written it out in this form here. Okay? Now, note that everything I have written it down in terms of VE. So what I'm saying is the following. We have to determine RB and RE. Now, I'm not going to determine RB directly. So what I'm transforming it is that first what I'll do is I'll choose a value of VE, the net emitter voltage at this particular point. I'll choose a value of VE, a suitable value of VE. Once I choose a suitable value of VE and I choose a suitable value of RE, right? Then what will I get? If I choose a suitable value of VE and I choose a suitable value of RE, note that VE by RE will give me the collector current or emitter current, right? And I know beta, so I know the base current, and thereby I will determine RB. So the way I'm designing it is I'm trying to find out how should I choose my emitter voltage here? How should I choose my emitter voltage here? And how should I choose my RE? On what basis should I choose? So I'm looking for equations which will allow me to make a right choice for the emitter voltage here. And similarly, will allow me to make a right choice for RE, given the information that I want 1 volt. Okay? So the same equations, let me rewrite them. This is what we have. I've added one more equation. One more equation, which is ICQ is VE by RE. Okay? So my design now, instead of directly, as I said, determining RB and RE, what we are going to do is determine RE and VE. Okay? All these four equations now, from the drive current, from the saturation angle, and from this one. Now, if you look at these two expressions, we have already seen that this one will always be, has more constraints than this particular one. Okay, so we need not look at this particular one. The second one we can rule out. Even before the second one gets violated, this one will get violated before that. Okay, so we need not look at the second term. All right, so let's apply to our problem. So in our problem, we are not given RE, we have to choose RE, right? We are given RL and we are given V0. So the first equation will become VE should be greater than or equal to 1, V0 is 1 plus RE I don't know, divided by RL. That's my first equation. The second equation we ignore. Third one will become VE less than or equal to 5 minus VBE 0.7 minus V0, which is 1. That is my second equation. And ICQ is VE by RE. Right? So let's write these down. This is what I've done. All right. How should I choose my VE and how should I choose my RE? All the relevant equations are there before you. I have to choose RE in fact, if you choose RE, then it decides VE. So the issue is, what value of RE should you choose? How do I decide? Or either way, if I choose VE, then it decides RE. So how should I choose? What should your objective be? If there are many possibilities, what should your objective be? Can I choose RE equal to RL? Can I choose RE equal to RL? Why not? if I choose RE equal to RL, what will this term be? VE should be greater than or equal to 2. This says VE should be less than 3.3. All right. So work it out. Let's see what answers do you get. These are the constraints now on VE here, and this is ICQ. So now choose a value of RE and choose a value of VE. Tell me what suitable values are. See, the equations don't tell us a unique value. They only, in design, you will only find constraints. And within the constraints will define a region. And within a region, you can choose the values. But the choice should not be arbitrary. The choice should not be arbitrary. Note that one of the things as a designer that you should do is, the user is asking for a swing of 1 volt. Supply is given 5 volt. Now your design should be such that you should draw minimum power from the supply. You should not unnecessarily use a value of RE and VE such that it's drawing a lot of power from the supply. So one of the objectives in your choice should be that if 5 volt is fixed, the power depends on ICQ. So I should use minimum possible value of ICQ. The higher the value of ICQ, the more the current you're drawing, the more the power you're wasting. It's not good. So when you are choosing your RE and VE, the objectives are to minimize the value of ICQ. Minimize the value of ICQ. So that gives you now, how do I choose my RE and VE? So this, if that becomes your objective, minimize the value of ICQ, that says use the highest possible value of RE, because RL is fixed. But if I use RE very large, what will happen? Can I use RE equal to 5 RL? If I put RE equal to 5 RL, this becomes 5 plus 1, 6. V must be greater than 6. This says V must be less than 3.3. I can't do that. So what is the highest value of RE that you can choose? Huh? All right. So in this case, I chose RE equal to 2 RL. I chose RE equal to 2 RL, 200 ohms. VE becomes, according to the first equation, 3.1. And this is 3.3. And I chose VE equal to 3.1. And then it gives me ICQ equal to 15.5. That's one possible choice. Well, if you're thinking maybe one should make RE such that VE here turns out to be exactly 3.3, right? You should leave some margins in design. You should not just push it so that both the limits are so close to each other that it will get violated. Always in design, leave some margin for error. We are not doing the most accurate calculation. There are things that are going to vary. So leave some margin here, okay? So when I said 3.3, I chose, our margins are very small if you look at it right now. I've chosen a VE of 3.1, and this says VE must be less than 3.3. So 3.1 is indeed less than 3.3, but what is the margin of error? 0.2 volt. 0.2 volt is the margin of error. That's a very small margin, okay? So, you know, in real life, in these analysis and in these calculations is fine. You can push it exactly to 3.3. Okay. But in real life, you'll have to give margins here. So this becomes our design then. So VE, we can choose, as I said, we'll try to choose RE as high as possible without violating any of the limits. One possibility is RE equal to 2 RL equal to 200 ohms. And then we choose VE equal to 3.1. And once we choose 3.1, And ICQ then, depending on RE, comes out to be 15.5. And we can calculate what is ICQ. We know is VCC minus 0.7 minus VE by RB into beta. And so this gives us RB of 7.7 kilo. So that completes our design. That completes our design. We have a value of RB and we have a value of RE. Let's see if you can choose for 2 volt. Design it for 2 volt. What would be the appropriate design for 2 volt? So go back and let me remove it. Let's say this is not 1 volt, but this is 2 volt. So redesign the amplifier if the maximum swing that you want is 2 volt. So let's keep this design here. This is 3.1, 15.5, 7.7K. Redesign it for 2 volt. So all these equations will change. V greater than V0. V0 would be 2 here. V0 would be 2 here. And same ICQ here. And on that basis, calculate.